Start the third session of the today. We have another talk from Professor Rick Kazman. He's going to talk about architecture in machine learning enabled system. Machine learning enabled system related with the model deployment, which is also related with the machine learning operation or ML loss, which is a hot topic, research and also industry. So let us welcome Rick again.
Thank you. Okay, so thank you again for inviting me. Thank you again for inviting me to speak. And for those of you who are graduate students or recently graduated, this is relatively new research for me, so I'm in your shoes. And whenever I embark on a new research project, I always remind myself of a quote from John von Neumann, who said, "Research is what I'm doing when I don't know what I'm doing." Right? Because if you knew what you were doing, it wouldn't be research. So this work is a result of collaborating with some data scientists for the past almost year and trying to figure out what's special about machine learning and about machine learning enabled systems, and what is it you need to know to architect those systems? What is it you need to know to work with data scientists? Because increasingly, these are the systems of the future. These are the systems of Web 4.0. Every system, I think, will be ML enabled in a decade or two. So the premise here is that if you include a machine learning component in your system, that has some architectural implications. Do we agree that that's true? Mostly? See, mostly nods. So, if we agree that that's true, and I think most people agree that it's true, well, exactly in what way does it matter, and what do we do about it? How do we work with those strange, exotic creatures, data scientists, to create something useful, something good, something of value? So again, my premise, my position is that architecture matters. That's what I built my career on. For all systems, not just machine learning intensive systems, but certainly machine learning brings its own non-trivial challenges. And so I want to explore those challenges. And there are a number of drivers in machine learning intensive systems that we as software engineers can bring a perspective to that data scientists may not have on their own. And so we need to work together to build these systems successfully, to build them at scale. So thinking about performance, scalability, integrability, testability, modifiability, maintainability, thinking about how to work with the constraints, legal constraints, regulatory constraints, cost constraints. Cost matters. We were discussing this, Bill and I were discussing this at the break, that a software engineer isn't a software engineer if they don't consider cost and schedule, the managerial side of developing software. It's not software science, it's software engineering. It means building real systems in the real world, in the end. And so if we ignore that, we're actually ignoring some of the hardest aspects of the problem. We have to think about deployment, and I'll get into deployment in a few minutes. There was a recent Gartner report that reported that 85% of AI projects fail, 53% never leave the prototype stage. So why do they fail? Well, maybe it's in the data science process. They just couldn't come up with a good enough data science algorithm, one that was sufficiently performant, one that was producing good enough results. But beyond that, there's deployment and there's evolution of the system. For the ones that that pass that prototyping phase. We now have to worry about turning them into real products and thinking about provisioning those systems so that they can perform well, that they are robust, that they can scale and be maintained. And this is where software engineering comes to the fore. And right now, I would say that this process is poorly structured. It's fairly chaotic. It's a chaotic world out there right now. There's a lot of ad-libbing. So, the way I see the world, if we're to have an engineering discipline of machine learning enabled systems, we need to identify the basic architectural challenges and the basic architectural primitives, the patterns and the tactics, so that an architect can work with a data scientist with an appropriate toolbox that they bring to the problem. And this includes asking the right questions of the data scientists. They don't know what they don't know. And so this has to be a conversation. So what I'm going to present is a way to facilitate that conversation. So what we've done over the last few months, we did a literature review, of course. Being good academics, we did an SLR. But then we talked to a lot of data scientists and a lot of architects of ML-enabled systems from Google, from FedEx, from some large banks, from companies that are building IoT systems. And we asked them about what architectural mechanisms they employed, what quality attributes they believe those mechanisms address. So why did you use this mechanism? Was it to make the system more secure, more testable, more scalable, more portable? And what were the costs and risks and trade-offs? So what I'm going to present to you now is a result of some of that investigation. Some premises. There is no one thing that you can call ML-enabled systems. It's highly variable. There's no single reference architecture. In some systems, ML is bolt-on. It's a side component. So if you think about doing a Google search, when you start typing words into that Google search, it will try and autocomplete for you, right? And there are lots of systems now that do this auto-completion. That's an ML component, machine learning component. That system is not critical to anything. Whether or not I have that type-ahead auto-completion might make me 2% more productive, maybe. So that's a system where, yeah, you could throw away the ML component, or it could be disabled, it could be down for a while, and nothing much matters. If you're working for Toyota and you're working on their self-driving capability or their accident avoidance system or the lane departure warning system, that has safety critical implications. That has to work. Another premise is that ML-enabled systems, surprise, surprise, are software systems. And so they share many of the same concerns that other non-ML-enabled systems have. And these systems are not monoliths. So we need to ask some questions. We need to have this conversation with the data scientists to find out how stable are the problem and the data over time. If you're dealing in an e-commerce domain, perhaps the problem itself is constantly shifting as competition is shifting, as new products enter the market, as customer preferences change, versus lane departure, where that problem is quite well described. How tightly coupled is the ML component with the rest of the system? So the type-ahead example I gave was a good example of not very tightly coupled. How much monitoring is required and how much is possible? How do you know when your system is going off, when its accuracy is going down, right? This is critically important. If you're a casino in Las Vegas and you're using facial recognition software and it's not performing very well, that matters to your bottom line. And you want to know when that system is losing accuracy. So there are these questions, and what I'm going to do now is talk about the different categories of questions that we have and how the kinds of conversations you need to have between the architects and the data scientists to appropriately engineer an ML-enabled system. So the first category is system-level concerns. These are concerns that apply to the entire system, the system as a whole. And the machine learning component doesn't have any special considerations. So every component, for example, should be tested, whether it's a machine learning component or not. Every component should be secure, whether it's a machine learning component or not. So these are system-level concerns. There are component-level concerns which are related to the needs of the machine learning part, but where these concerns are non-local. Right? So if something is localized in a machine learning component, as an architect, I'm okay with that. Right? That's that component's problem. But if that concern affects other components, and we were talking about this at the break, if an assumption made in this component is going to ripple to another component, if accuracy falls here and that's going to affect the prediction that I make over here, then that's non-local. And we need to understand that. So drift rate and the nature of drift are examples of non-local concerns. Model retraining and the cadence of retraining and the amount of effort you need to do to redeploy. These are non-local concerns. Data transformations. How much do you need to smooth and massage and filter data prior to prediction? These matter. So we're interested in the architectural implications of the ML component. The third are system environment concerns. So this is about how should you provision the environment in which this ML component is going to operate. So you need to provide appropriate levels of resources, CPU, memory, bandwidth, to the system components. There's no point deploying a really complex AI model on an Apple Watch, right? You have to have an appropriate match of the computational needs to the... And finally, there are machine learning specific concerns. So these may be required for proper functioning of the system, like privacy or fairness. But the solutions to these concerns are ML specific. That is, they don't live in the architecture. With the same architecture, I could build a fair or unfair machine learning component. Right? That has to do with the choice of data set and how that's vetted and how I sample the data and things like that. So what we've done is put together a questionnaire. And these are a set of questions that an architect can use to talk to data scientists and domain experts in order to better understand the nature of the system, the requirements of the system. And so for each category, we provide questions to the architect and examples of possible answers to stimulate discussion. And this is a well-established elicitation technique. So we've done this sort of thing in other domains of architecture. So for example, to elicit quality attribute concerns from stakeholders, to ask people about security or testability or modifiability or things that non-software engineers don't often think about but ought to. So it's a well-established technique. Okay, so let's look at each of these in some detail. So the system-level concerns, these are the things that are related to the proper functioning of the system, but they're not ML specific. So security, performance, modularity, maintainability, availability, testability. These are all system-level concerns. So the first question, time sensitivity. How important is it that predictions are produced at a specified interval or by a specified deadline? How does prediction time influence system performance as a whole? So examples at the endpoints, you might have a BI dashboard where inference deadlines are very loose. You could have very high latency, low time sensitivity, versus image-based navigation, where there's going to be a fixed GPS polling rate, and if you don't come up with a prediction in appropriate amounts of time, the system is a failure, right? So that's important. Data quality. Can the system detect and adapt to different levels of data quality, and can this be done dynamically? So one example would be a fraud detection system where inputs will typically come from databases of record, and you're likely doing very little checking, and so any errors in the inputs are just going to propagate, versus an IoT monitoring system where detecting sensor quality or misuse of sensors is going to be really important, and it's something that can be done locally. Model modularity. So this is, again, a topic we were discussing briefly at the break, and this is a really hot topic in machine learning, or at least in the software engineering of machine learning enabled systems. So how tightly coupled is the model to the rest of the system? How stable are the APIs? If the model algorithm change, do the interfaces to it change? Remember I talked before the break about unstable interface, right? That's an architecture flaw. You don't want that to happen. Is there a choice of algorithms? Does the data scientist have a choice of algorithms? And are those algorithms supported by more than one machine learning framework? Are the APIs that they provide compatible? Right? So think about ripple effects of a change. If the data scientist chooses a different algorithm, chooses a different framework, chooses a different kit, then are there going to be significant ripple effects? Are other components going to have to change as well? Are the discrete tasks well understood, cohesive, well supported, like in computer vision, where there's standard techniques in the data processing pipeline? There's segmentation, edge detection, bounding boxes, object detection, and these are well understood, cohesive, and well supported, perhaps not so much in other domains. So this is going to be a really important conversation with the data scientist to manage complexity in the systems. So, an example of the first kind is text classification. You might have several alternate algorithms that you could use to solve the problem, and some of those are supported in multiple different frameworks. So you could use scikit-learn, you could use TensorFlow, you could use PyTorch, and so you have options. And so if your system is like text classification, then you can abstract the problem from the model. And you can package the model with low coupling to the rest of the system so that it's easy to change that implementation toolkit. For other problems, additional dependencies may make modularizing the model more important. So there may be several special purpose models chained together, and so you can't change one without changing all of them. What about portability? How easy is it to move your model, your implementation from one platform to another, from one cloud provider to another? It's common to only train and serve models on a single provider, a single cloud platform, but lots of companies may want to have the flexibility to port their model between cloud providers, because the cloud, while really convenient, is expensive. And this is becoming a dominating cost. It's something that a lot of companies are now starting to pay attention to, the increasing amounts that they're paying to Google and Amazon and Microsoft for cloud services. Testability. Can you independently verify the output of an ML model? Can you judge it based on false positives and false negatives, right? This is the core of testing in traditional software systems. But it's not always so easy in machine learning systems. One of the ways in which we improve the testability of traditional software systems is by capturing system states and intermediate results for fine-grained testing. Right, we have observability frameworks, things like that. But that's often not part of it. How do you reach into a complex, multi-level neural network and grab an intermediate result? Right, you can't. Not unless you have specifically engineered another machine learning component to observe that neural network or certain hidden layers of that neural network. So you may want, for example, to test conditional estimates within a model, like accuracy by race. Right? This has become a hot topic in machine learning classification algorithms. Or business logic. You may want to test different kinds of business logic assumptions in your market. If you're doing fraud detection, what are the check hold times? Related to testability is monitorability. So testing is what you do before you deploy your system, and monitoring is what you do after you've deployed your system. But they both are getting at the same thing. Is my system still properly functioning? So can your ML components be monitored at runtime? Is there a single monitoring component? Do you need to deploy additional components to monitor your system? And the examples here are you might want to monitor system resources. How much CPU are we using, and how much headroom do we have? How much bandwidth is available? How much memory is available? Typical system resources versus machine learning specific measures of prediction accuracy, change in the distribution of the data as compared, the observed data as compared to the training data, emergence of new edge cases or new classes that haven't been predicted. So these things are often very important to monitor. Okay, so now let's turn to component level concerns. And remember, these are concerns that involve the machine learning components that have non-local effects. So one of these is the retraining cadence and deployment effort. How frequently do you think you're going to have to retrain and redeploy your machine learning model? And how much are these deployments automated? So at one end of the spectrum, we have medical devices. If you have a blood glucose monitoring system, you maybe have one deployment a year. That deployment has to go through significant testing and approval by, like in the United States, it'll be the Food and Drug Administration. So one deployment a year is as good as it's going to get. And you probably do that manually with a great deal of human oversight and supervision. Versus a recommender system. If you're Netflix, you're pushing out new versions of the recommender system regularly, perhaps daily, and ideally with low or zero human effort and intervention. What's the drift rate of the data? Is it expected that the data might drift over time? Are the conditions of drift predictable? Do you need to monitor these conditions? Is this going to be distributional drift, concept drift, or both? And again, the examples might be blood glucose readings at the one end, not likely to drift very much. Blood chemistry is what it is. Versus consumer preferences. New products come to market, a new influencer starts promoting some new product, changes the seasons, things like that. These can be quite dramatic and rapid in response to changing environmental conditions. Third is system environment concerns. So how do you provision the environment for your system, and in particular for the ML function? So is this functionality within the system going to be federally, fully centralized? You have Big Blue, you send some data to Big Blue, it comes back with a prediction. Federated, where you might have a centralized model interacting with edge devices. So my phone knows how to recognize my face and perhaps a few other things, but if I ask it to recognize other things, it has to go back to a centralized learning model for the prediction. And fully decentralized, where each node of the system is up here, so some kind of highly personalized federated learning. What's the computational intensity of the training effort in terms of time and space? And this, of course, may be a function of the inherent complexity of the approach and the size of the data set. So examples, ordinary least squared is order n, n is observations, n is features in time and space. Random forest is order t, m, n log n in time, order m, d in space. You can read the parameters there, right? So you have some dramatically different choices in terms of the amount of computational power needed. And this is also true at prediction time. What's the computational intensity of the prediction? And again, ordinary least squared, low, random forest, might be a little bigger. And then, irrespective of the computational intensity of the algorithms you have chosen, what's the computational power of the platform on which you're deploying? Right? Is it a good fit or a bad fit? So, am I trying to deploy to a single IoT device? Or maybe a GPU or NPU cluster hosted in the cloud? Right? Dramatically different options. So I said we've been talking to a lot of architects. One architect we talked to was deploying machine learning systems in homes where they're interested in determining things like, is your toilet overflowing? Right? They have lots of little sensors in a home, each of which has its own machine learning component, and each of which has to determine, oh, this is high humidity, but that's just because someone's taking a long shower, versus you have a flood in your bathroom, right? Those conditions look very different to us. They may not look that different in terms of the readings on the sensor. Data fusion. Where does the information come from? How many sources or sensors need to be composed into a single representation before it is presented to the model, and will these change in the future? So something that would have a relatively stable and simple data fusion might be fraud detection, where you would have your own database, but perhaps a database from a government source, like in the US it would be the Treasury Department, versus cookies for user behavior, again, which can be very dynamic. You may be looking at many different cookies from many different data sources, and then these will change over time as user preferences change. Analytic redundancy, here's one that almost nobody thinks about, but is a really powerful option for the architect. So is there a requirement for a redundant component or set of components to provide additional sources of information or truth, perhaps with lower accuracy and less demanding performance characteristics? So if my ML model isn't working, can I fall back to an expert system? If my ad placement engine is not working, can I just serve a random ad? Right? So the idea here is that you have, if your ML model has performance limitations, if there's a chance that it may fall outside its happy operating window, can you fall back to a more reliable, less demanding component as a fallback? So the example in the real world might be, if the anti-lock brake system in your car fails, you still have your right foot. Your right foot, yeah, that's right. Right, so there's a fallback system that you can fall back to for safety reasons. What amount of data does the system have to ingest and to process to produce predictions? So, you know, at one end we might have high-res satellite images or high-definition video. At the other end, maybe a hand-created Excel file. And finally, there are these ML-specific concerns, which are important to overall system success, but they primarily live outside the architecture. And it's important to understand, this is not my job. as the architect, right? It's important to understand what's in scope and what's out of scope for you. So things like privacy and fairness are really important, but they don't seem to depend much on architectural choices. Ethics would be another example. This is more about how the data set is chosen, how the algorithms are trained, perhaps bias in those. Now you may want to monitor these, that would be an architectural concern. You may want to test these, that would be an architectural concern. The concern itself lives outside the architecture. Regulatory considerations. These only become architectural concerns if they are complex enough that they require their own or additional architectural components. So a good example of that would be license plate information. If you are running a highway that charges cars by the distance driven, then you need that license plate information for billing, but other information, the person, their location, would need to be scrubbed from that data if you were going to share that for, let's say, statistical purposes, for convincing the municipality you need to add a new lane to the highway or something like that. So if you're using computer vision to determine the license plate, that has to be part of the data set for one use, but not part of the data set. You need to partition the data set for other uses. A system that processes facial images and wants to enforce some standards for fairness has to very carefully design the monitoring and sampling strategy, but this could be handled entirely by the data modeling effort that's completed before the model is deployed. Right? So that would be an example of non-architectural concern. Okay, so the good news is that most of these concerns are not unique to machine learning enabled systems. These are pretty much standard software architecture. So I'm making a shameless plug for my book here because we have 10 chapters in this book on quality attributes, on performance and modifiability and testability and security and availability and all of these abilities. And all of our existing patterns and tactics apply, which is the good news. The biggest challenge, I think, is model modularity. So what's the purpose of this? As I said, the purpose is to provide an elicitation device, a means of having a conversation between an architect and data scientists. And in the workshops that we've done so far, where we deployed this questionnaire, the architects said that this would have saved them weeks of effort had they had these questions at the beginning of their process, because they were things that they only learned via trial and error and via making bad decisions and having to withdraw them and redo them. And so there was a lot. This can save a lot of rework effort, which should be our goal as software engineers, to try and improve quality and lower costs to improve predictability. So that's it. I'm happy to take questions now.
Thank you very much. Any question? I assume there will be a lot of questions. Who is going to ask the first question? Go on.
Hi, thanks for this nice talk. Really interesting. I totally agree that model modularity is like a very huge challenge. Do you have some first insights how an interface should be designed that maybe in case data changes, for example? Like that is a huge pain point for model modularity.
Sorry, can you say what was the huge pain point?
Model modularity, as you stated.
Oh, yeah.
I totally agree with you. And do you have some first insights how an interface should be designed, or how one could avoid this pain point of modern modularity?
Yeah, I don't have any silver bullet, unfortunately. I think that this is an emerging research area. I think that we're all just trying to figure this out right now. I think that asking the right questions is the beginning. So even just asking about cohesion, for example, why are you computing these two functions in the same component? Or why is this one function being distributed across 5 components? It can go a long way to understanding the mapping between functions and their realization components. Also, trying to explicitly identify the dependencies between the models and the APIs that are used can be a guide to this. But really, these are just my early insights. As I said at the beginning, research is what I'm doing when I don't know what I'm doing, and that's clearly the case.
Thank you.
Maybe just pose it at mic. So my question was, in this series of workshops that you guys ran, because we had this discussion before, and you've had like 4 or 5, a number of them, have you encountered patterns of solutions that these people apply, but also what is their background? Because our experience, for example, is that many of these data scientists, they are not drawn from computer science, in fact, right? So they are adapted to be data scientists, so-called data scientists, and one of the things we figured out is they're short of data engineers, so the people that help them put things into production. So what is the background, and is there a pattern emerging?
So what I've been finding is, we've had 4 of these workshops so far, and mostly we've been talking to data engineers that have been forced into becoming architects, which was not their training. And they, as I said, by and large, they didn't think of these issues early or early enough. I'm trying to think, were there patterns of behavior? In one case, there was one architect who did try and actively use tactics and patterns. He did think in terms of standard approaches to managing performance, so, to managing the event rate, to parallelizing, things like this, sort of software engineering approaches. But by and large, these people were doing, these architects were doing trial and error. It was a very inefficient process. As I say, they tended to have much more experience with data science than with software architecture.
As well. Makes sense.
Yeah. So, the good news is this is fertile ground. There's people out there that need our help.
Yay! We matter.
We matter.
Thank you. When you talk in the workshops to the people or to the participants, was it possible to figure out that there are various groups of, let's say, enabled usages? Yeah, sometimes it's just for decision and the data is fixed or things like that, and sometimes it's more on the data flow model. Is there something like this that you could find? And then from that, look for patterns or other commonalities.
So we're not there yet. We don't have enough data points yet, but we've certainly seen, as I said in one of the first slides of my talk, there's a huge variation in what people were using ML enablement for. So on the low end, very close to the device, as I say, were IoT systems, where they were really worried about very low level data smoothing, trying to come up with subtle predictions based on a noisy data stream. On the other end, we talked to architects at Google, for example, where they have enormous resources, almost infinite resources, where they can simply throw a model over a wall to a deployment team. These data scientists don't need to know anything about deployment. We've also seen instances of companies that are using machine learning almost as an internal expert system, let's say. So for example, FedEx, the package delivery company, they have this complex ML system which they feed in all kinds of parameters about anticipated package volume and historical trends and things like that. Weather conditions, these can affect, upcoming holidays can affect it. And then it'll spit out some recommendations, and then a person looks at those, and a person makes decisions. So the system itself isn't connected to anything. It's just an advisor to an expert. So, as I say, I don't have enough data points yet to really properly answer your question about whether there are commonalities, but our goal is to look at more and more of these examples so that we can associate requirements on the one hand with kind of solution archetypes, patterns, and tactics on the other hand.
So I agree that standard software engineering has a lot to offer to this field. I think one challenge that is unique is the problem of reproducibility, especially with this try and error, playing around with approach, where people often don't remember how they got to the point where they are and whether they now got whether they have a consistent pipeline. And I think that is something that would require targeted solutions, because we don't have that so much in traditional software engineering.
I think that's a fair comment, that even in traditional software engineering, we have not placed a lot of emphasis on reproducibility. And as you say, the ML models, many of which are black boxes by and large, exacerbate this problem. I think that that's why we put in several questions and a focus on testability, monitorability, drift rate, those kinds of things, to emphasize to the architect, you maybe want to think about these things early so that you, for example, capture intermediate results or have some observability window into the hidden layers in your neural network. So I agree with you, it's a big problem, and I think that we're still trying to understand the solutions to it.
Hi, thanks for the presentation. So I'm coming from the AI planning community, where I dared to submit a paper that would say that planning systems should become modular and they can be composed so that we can get from the prototyping phase to a production phase, and I was slammed because of that. So basically, this is just because at least in the AI planning community, engineering of systems is seen as engineering data models and algorithms, and maybe domain models to represent the application. And this is very orthogonal to software engineering practices. So in order, for example, to support modularity, we need the expertise from the, let's say, AI planning community, and the same from the machine learning community. But if there is no ear for this, what to do? I mean.
Yeah. So this relates back to my talk before the break, which is, if you cannot come up with a cost-benefit argument, you're going to be in your unfortunate shoes. of saying, people, we should do this. It is the right thing to do. And people don't want to hear it unless you can make a money argument to them. So what you need, my advice to you, is to look for the counterexamples, or to gather data about how much it costs people in rework and refactoring that could have been avoided had they taken a earlier, more proactive approach to modularity. This is the problem that all software engineering faces, right? You remember my picture of the guy paddling, right? But I think it's worse in machine learning community because these are shiny new toys. And we're getting such value out of even crappy models, single purpose models that aren't very modular and aren't very flexible, that it's hard to make a case for improvement, right? So that would be my advice to you, is to try and capture cost and benefit data. If you can do case studies of projects that have not taken this approach and how they have suffered, and they have, I'm sure that would be my recommendation. And that's sort of what we did in the early days of my research on software modularity in the DR space. So we looked for the companies that were suffering.
Yeah, thanks again, Rick, for the interesting talk. Now we move into the last session. It's a paper session. We have 3 interesting